So, Section 1.5, elementary matrices and a method for finding A inverse. On last time we talked a little bit about the elementary matrix, a very simple matrix that is found by performing only one elementary row operation to the matrix or to the identity or from the identity matrix. So the elementary matrix is a very simple concept. First thing we want to do is to prove what I call the monster theorem. And that's a theorem that we will begin with here in this section, and then as we go throughout this course, we will add other equivalences to this particular theorem. Again, a very important theorem is that every elementary matrix is invertible, and then also the inverse of an elementary matrix is also an elementary matrix. We'll need that for what I call the monster theorem. Here, the way we prove equivalence theorems is that we assume one to prove another, and then once you prove that, we assume that to prove another statement of the equivalence, and then we assume that conclusion to prove something else. And what you want to do is to be able to go in a round. So we're going to assume A to prove B, and then after that, assume B to prove C, and then assume C to prove D, and then assume D to prove A, and you get a complete round. Now, you don't have to start in that order. You can start anywhere. You can start by saying assume C to prove A, and then just as long as you have all of them, inferring from one statement to another, where you have an inclusive argument that includes all of these statements. So one implies the other, and so then even the conclusion of the conclusion should imply even the first initial statement. So I will just take it straight as it is and assume the first part, assume that A is invertible, to prove that the system AX equal to 0 has only the trivial solution. So here we assume A, that is, given that A is invertible, prove that AX equal to 0 has only the trivial solution. Well, if A is invertible, then we know that simply that A inverse exists. A inverse exists. Well, we're not assuming that AX equal to 0 exists. We're given that, but we want to show that AX equals 0, its system, that the solution gives us only the trivial solution. Well, it's very simple. It's simple if A is invertible. So if A is invertible, then A inverse exists. So multiply both sides of AX equal to 0 by A inverse, and we get it. So here, this implies that A inverse times A times X is equal to A inverse times the 0 matrix, right? This implies that we have the identity matrix times X is equal to the 0 matrix. Now, notice here that the identity times x this is what this statement means. The identity times x equal to 0. So this implies then that x sub 1 is equal to 0, x sub 2 is 0, and so on. X sub n is 0. Hence the trivial solution. So that's finished. So now we assume that ax equal to 0 has only the trivial solution to show that the reduced row echelon form of A is the identity. So here, now assume that if ax equal to 0 has only the trivial solution to prove that the reduced row echelon form A is indeed the identity. So here, since ax equal to 0 has only the trivial solution, we have this. Just write out ax equal to 0. So that is a11 times x sub 1 plus a12 times x sub 2 plus and so on plus a1n times x sub n is equal to 0. A21 times x sub 1 plus A22 times x sub 2 plus and so on plus A2 sub n times x sub n is equal to 0, and so on. So this is a square matrix, so this is n by 1 times x sub 1 plus A sub n 2 times x sub 2 plus and so on plus A sub n times x sub n is equal to 0. Now this is the system here, ax equal to 0. Since we know that it has the trivial solution, then what that gives us is that a11 times x sub 1 is equal to 0. A22 times x sub 2 is equal to 0. And write down the diagonal. So here, this implies that we have a11 times x sub 1 is equal to 0. A22 times x sub 2 is equal to 0, and so on to a sub n times x sub n is equal to 0. Now, what is that? Well, this gives me the so-called trivial solution. That is, I have x sub 1 is equal to 0, x sub 2 equal to 0, and so on, x sub n equal to 0. But doesn't that imply, that implies that we have, in terms of the matrix, 1, 0, and so on, 0, 0, 1, 0, and so on, 0, 0. The diagonal is 1. Get 0, 0, and so on, 0. I mean, this, the trivial solution implies that this is what? This is the identity matrix, right? Here with 0, 0, and so on to 0. Or better yet, this is the identity matrix times x equal to 0, and this implies the identity matrix. The identity matrix times x equal to 0 just gives us the x sub 1 equal to 0, x sub 2 equal to 0, and so on to x sub n equal to 0. Well, if that be the case, let's see, where are we in the Monster theorem? So now, I forgot to write assume, this is assume A. Now assume that here, here assume B to prove C. We assume here A to prove B. Now we assume C to prove D. More space. So now we assume C to prove D. And C said that if the reduced row echelon form of A is I, then does that mean that A can be expressible as a product of elementary matrices? Let's see. Well, let's see. So we take what's given, and what's given here is that A is reduced and can be reduced to the so-called identity matrix. Um, so here, if A can be reduced to the so-called identity matrix, how do we do that? We reduce A to its identity by performing a single elementary row operation to A each time to such that we produce the identity matrix. Do you feel what I'm saying? So give me the matrix A. I'm going to reduce that. Remember that process we said we take A, 1, 1, and get zeros below it? Well, each time you did that, that was an elementary operation. And so simply said, the operation is said to be an elementary matrix. So I can multiply the matrix A by an elementary matrix that reduces A one time, and then after that, I'm going to perform another operation, and I'm going to keep on performing these elementary row operations until the original matrix A ends up looking like the identity matrix. So let me write that out. So here, if A can be reduced to I, then here the process came about by multiplying the matrix A by a single elementary matrix. Here, how many times we do it? You do it some k times, some r times, whatever, how long it takes to reduce that. So we do this by a single elementary matrix here, k times, to produce I. Well, let's write it out mathematically. That is, I have the matrix A. I'm going to multiply it by an elementary matrix. One time, I'm going to multiply it by another elementary matrix. Each elementary matrix represents a single elementary row operation. We're going to do it k times. What's the number k? It could vary. Once I end up, I produce the identity matrix. But notice here that it says that if A is reduced to the identity matrix, then A is expressible as a product of elementary matrices. Here, what I've done was to only express the identity matrix as a product of elementary matrices times A. So I still don't have what I need. What we're trying to prove, it says to assume that A is reducible to the identity matrix. Well, that's the assumption. That's the statement here. I haven't proven anything. To prove that I can write A as a product of elementary matrices. Now, how do I do that? In other words, get A by itself. That's all they're saying. well, I need a fact. I need a corollary. I need a lemma, some axiom to tell me how I can break this down. We have it. Here's the theorem. Every elementary matrix is invertible, and the inverse is also an invertible matrix. So if I have an elementary matrix, this theorem says that its inverse exists. Every elementary matrix is invertible, right? And the inverse is also, so if I get the inverse of an elementary matrix, that inverse is also said to be an elementary matrix. That's the key. That's the key to the puzzle. So let's call this, it's a theorem, but let me call it a lemma. Oops, didn't work through it. A lemma is said to be a theorem that supports another theorem. It's like a minor theorem that's used to support a major consequence, a lemma. So using the lemma, that every elementary matrix is invertible with the inverse also being invertible, to write, taking the statement right here, the lemma says this, that this elementary matrix E sub k is inverse, exists, and its inverse is also an elementary matrix. So here's what I want to do. I can multiply left multiplication on each side, left multiplication over here, left multiplication over there, by this inverse of this matrix, because it exists by the lemma. Every elementary matrix is invertible, right? And then once I do that, then I take the next elementary matrix, I multiply both sides, left multiplication by its inverse. Keep on doing that. How many times? K times. And then I end up on the left side with just A standing all by himself. He's the last man standing. That's what I want. So here, what we have, write the first one out, and then after that, we'll just do the sequential statement, and we have it. So this is the inverse of E sub k times E sub k. Let me put the next one there so you can see it. This is E sub k minus 1 times, and so on, times E sub 2, E sub 1 times A. This is equal to, I'm multiplying by left multiplication of the inverse of E sub k times the identity. So when I do that, because a matrix times its inverse leaves me the identity, so here, this leaves the identity times E sub k minus 1 times, and so on, times E sub 2 times E sub 1 times A. That's equal to E sub k, the inverse of that, times the identity. So now I'm going to multiply each iteration of E sub k minus 1 is inverse to both sides, and then I'm going to multiply to both sides the inverse of E sub k minus 2. Do that until I end up with just A on the left side. Then I have a string of matrices multiplied on the right side, and they're all elementary matrices. So here This is E sub k minus 1. This identity times the matrix is just the matrix, so let me just write that. Times, E sub 2 times E sub 1 times A here, I multiply this guy by the inverse of E sub k minus 1 times, and so on, times E sub 2 times E sub 1 times A is equal to, now let's go ahead and just well, I better write this, but I didn't put this guy there, E sub k minus 1 times, and so on, E sub 2 times E sub 1 times A. This is E sub k minus 1, the inverse of that, times the inverse of E sub k times the identity. I think you get the picture, so I'm going to say dot, 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 and so what I end up with is A is equal to the inverse of E sub 1 times the inverse of E sub 2 times, and so on, times the inverse of E sub k minus 1 times the inverse of E sub k times the identity. The matrix A is expressible as a product of elementary matrices. Because the lemma said that the inverse of the elementary matrix is itself also an elementary matrix. So now the last part is to assume D to prove A. So lastly, we assume D to prove A. Oh yeah, by the way, this proof is on the test. No sense to me going over it if I didn't expect you all to know it. So here we assume D, that is this last part, that A is expressible as a product of elementary matrices. To prove A, well, A said that the matrix A is invertible. So here, assume that A is expressible as a product of elementary matrices to show that A is invertible. So we can't assume that A is invertible anymore. We don't know that. All we know is that A can be expressed as a product of elementary matrices. Well, I know this statement here. This is what I know. Well, if A can be expressed like that, so here, given that A is equal to the inverse of E sub 1 times the inverse of E sub 2 times, and so on, times the inverse of E sub k minus 1 times the inverse of E sub k times I. here A is equal to the product of these elementary matrices, which implies this, that these guys have to exist. Each individual elementary matrix has to exist to be able to give me the final product of A. Right? They exist. Since they exist, and we know that these elementary matrices, their inverses also exist. Not A. Each individual matrix here, elementary matrix, their inverses exist. So this statement here implies basically how we got it. This statement here implies this statement. Given that this is the case, which implies also by the lemma here, the inverse, the first statement, the statement here. That's what I'm after. That is, if I take this statement and multiply each side, left multiplication, by each of these inverses here, starting with e sub 1, I end up with what I started out with here. So this gives me e sub k times e sub k minus 1 times and so on times e sub 2 times e sub 1 times A is equal to the identity matrix. Now that statement really has the answer, that if I have a matrix times another matrix and that equals to the identity matrix, then that means that here the inverse of this matrix is the matrix that's multiplied to it. And let's take here that the product of these elementary matrices is one matrix, which it is. Once you multiply them all out, I get one result, I get one matrix. So we said that by the definition of the inverse, if I have a matrix times another matrix equals to the identity, then here, if it's A times B equal to I, that means that A inverse is equal to B. Well, here this is acting like B. So here we say, so by the lemma we get this, and by the definition of an inverse, A inverse is equal to e sub k times e sub k minus 1 times and so on e sub 2 times e sub 1. So that's the monster theorem. Now what we'll do, I think the next statement that we'll add to this, to the monster theorem, point number 5 would be that the matrix A, its determinant, is not equal to 0. And then that'll be the sixth guy that you put into this claim. So we'll take D and assume D to prove E, but it doesn't matter which way you move in that circle. I think to show that the determinant is not equal to 0, it's probably easy to take the fact that that A is invertible, and you get what you want, or that the matrix A is reduced to the identity. Yes, that's it. And then take the determinant of the identity matrix, and that gives you 1. That's not equal to 0. So that'll be an easy way to prove that. But anyway, make sure you know that. here's the method to find an A inverse. We're going to write the matrix that we're starting off with, the matrix A, on the left side, juxtaposition with the identity matrix on the right side. Perform a series of elementary operations to the system. So whatever you do to A, we do that same thing to the identity matrix. The goal is to reduce the matrix A to its identity with the process of elementary row operations. But whatever you do to one side, do the same thing to the other side. And so if you can reduce A on the left side to the identity, then what you have left on the right side will be A inverse. And like I said, if all goes well, you should have this, right? If all goes well. Now, it should have been a number 6 there. And I should have said for number 6, check A inverse times A to make sure that equals to the identity matrix. That's the way you can check to make sure that you got the right thing. Okay. All right, let's look at this problem here. Find the inverse if it exists. So we're going to use that process up above. So on the left side, we have the matrix A. And then on the right side, we have the identity matrix. And with a series of steps, we want to end up with the left side being the identity matrix. And then hopefully on the right side, we get the inverse. So we're just going to reduce the matrix on the left side to the identity, what we've been doing before, but do those same operations over on the right side to this identity matrix over here. So the first thing we're going to do is to have a leading 1 there at A11. So we're going to interchange rows 1 and 2. So now after that, we're going to take this leading 1 to get zeros below it. So we'll say negative 3 times row 1 plus row 2, and then negative 2 times row 1 plus row 3. Row 1 stays the same. So it gives us a 0, 4, negative 9, minus 1 is negative 10. We get 1 there, negative 3, 0. Here we get 0, negative 2 times 0 is 0, plus 5 is 5. Negative 2 times 3 is negative 6. Minus 4 is negative 10. Then negative 2 times 0 is 0, plus 0 is 0. Negative 2 times 1 is negative 2. Plus 0, we get negative 2. Negative 2 times 0 is 0, plus 1, we get 1. So the next thing we want to do is to get a 1 at A22. Bless you. Now, what I'm going to do is I'll try to save the fractions to the end if possible. Sometimes that's not the case, but if I can hold off on the fraction till close to the end, by all means, let's try that. If not, you can just divide everything in row 2 by 4. That'll give you a 1 and negative 5 over 2 and 1 over 4 and negative 3 over 4 and 0. So we can offset that by, I'm going to say negative times row 2 plus row 3. That'll give me a 1 here, and then after that I can interchange rows 2 and 3. So here, negative times row 2 plus row 3. So 0, 1, 0, negative 1. This is 3 minus 2 is 1, and then 0 plus 1 is 1. Now we interchange rows 2 and 3. Now we can use this 1 at A22 to get a 0 below it. So negative 4 times row 2 plus row 3. Zero, 0, that stays negative 10. But 4 plus 1 is 5. Negative 4 minus 3, negative 7, and then just negative 4. Well, we got a fraction there, so nothing we can do about that. So we divide everything in row 3 by negative 10. Gives us negative 1/2, 7 over 10, 2 over 5. So now the last thing, the negative 3 times row 3 plus row 1. It's going to give us the identity here. Rows 2 and 3 stay the same. All right, so here we say negative 3 times negative 1/2, which is 3/2, plus 0, we get 3/2. And then negative 3 times 7 over 10, so it's negative 21 over 10 plus 1, or just 10 over 10. So it gives us negative 11 over 10. And then negative 3 times 2 over 5, which is negative 6 over 5, plus 0 just gives us negative 6 over 5. So now the question is A inverse equal to this 3 over 2 negative 11 over 10 negative 6 over 5, negative 1, 1, 1, negative 1/2, 7/10, and 2/5. Well, we don't know. We have to multiply the matrix A times A inverse to see if that actually works out. So let's see, I got A inverse sitting there times A. 3 over 2, negative 11 over 10, negative 6 over 5, negative 1, 1, and 1, negative 1/2, 7/10, 2/5. Now times the matrix A. So going back and forth for some years, okay. Three, 4, negative 1, 1, 0, 3, 2, 5, negative 4. So we do here first position, first row, first column. So it's this row times this column. Let's use this as a scratch part. So this becomes 3 over 2 times 3. So it's 9 over 2. Then it's minus 11 over 10. Then it's minus here 6 over 5 times 2, or negative 12 over 5. So 2 goes into 10 5 times. So it gives us 45 here, minus 11, and then 5 goes into 10 2, and that gives us a 24 minus 24. So we get 45 minus 35, so that's 10 over 10, that gives us a 1. Right? Well, that's good so far. Let's check the rest of them. The second position, this is the first row, second column. Remember, for the first matrix, for matrix multiplication, you always multiply the rows. And the second matrix is always the columns, row times column. So this is A1, 2, so this is the first row, second column. So that's 3 over 2 times the 4. That becomes here just 2 times the 3, we get 6. And then this is 0, and this is minus 6, 0. Right? Let's check the first row, third column. So that becomes negative 3 over 2 minus 30 over 10, or just 3, if you will. We'll leave it like that. That's fine for right now. And then here, plus 6 over 5 times 4, 24 over 5. So we get 5 times negative 3, negative 15, minus 30, plus here 48. Let's see, where did we get that from? That was first row, second column. That's Oh, I'm doing the wrong one. First row, third column. Yes. So it's negative 33. Yes. That helps out a whole lot. So that gives us 0. Woo! Yeah. So let's go and check the other one. This is the second row, first column, second row, first column. So this is negative 3 plus 1 plus 2, that's 0. Good. Second row, second column. So this is negative 4, 0 plus 5, that's 1. Second row, third column, you get 1 plus 3 is 4, minus 4, 0, that's good. So now it's the third row, first column, so negative 3 over 2 plus 7 over 10 plus 4 over 5. It's 10, 5, negative 15 plus 7 plus 8, well, that's 0. And then the third row, second column, so that's just negative 2, that's 0, and then this is plus 2, we get 0. Then the third row, third column, so we get 1/2 plus 21 over 10 and then minus 8 over 5 get 5 plus 21 minus 16 . So gives us 10 over 10, you get 1. That checks out. So indeed, the inverse is this guy. Now, let me, because my time is of essence, I would need you to do this second one. Let me give you the inverse. And so when you work it, don't have time to do it now, but you can do it later. A inverse comes out here to be this matrix, 3 over 7, 2 over 7, negative 4 over 7, 2 sevenths, negative 1 over 7, 2 over 7, negative 4 over 7, 2 over 7, 3 over 7. You can work that and check that and see if that's what you get. Number 3. Yes, sir. Okay, let's look at number 3. So here, what I'll do is use this negative 1 to get rid of this 2, and then use that negative 1 to get rid of that 4. So here we have 2 times row 1 plus row 2. And I think what I did was, I think I used this 2 to get rid of that -4 instead of multiplying by 4. It doesn't matter. So let's say -4 times row 1 plus row 3. So the first row stays the same. This becomes 0. 6 and 4 is 10. And this is -8 plus 1, -7. And then 2 times 1 is 2, plus 0 is 2. It stays the same, and this stays the same. So -4 times the -1 gives us a 4, minus 4 is 0. -12 plus 2, -10. We get 16 here, minus 9. We get 7, and then we get here -4, 0, and 1. Now, multiply or add row 2 to row 3. I want to get rid of this 10 down here. You know, get a 1 here where that -1 is, and then we move to the 10, supposed to get a 1 there, then use that 1 to get zeros above and below. But since there's commonality with the 10, -7, and the -10 and 7, let's just get rid of that -10 down there. Let's see what happens. So here, just simply say row 2 plus row 3. And if you want, you can go ahead and say negative times row 1 as well. So it's 1, -3, and 4, -1, 0, and 0. This is 0, 10, -7, 2, 1, and 0. We get 0, 0, 0, -2, 1, and 1. All right, what do we do next for this problem? Do you see a problem? Yeah. We got all zeros right here. So the question is, can this left side become the identity matrix? No, I can't produce it. So thus, if you get that, we say no inverse exists. You're done. So anytime you have that, there's no inverse. All right, okay, 4. So let's see. We take this 1 to get a 0, where that 1 is down there. So just say negative times row 1 plus row 3. So now at A22, we take that 1 to get a 0 below. So we simply just say negative times row 2 plus row 3. it's just a negative 1 there. And then that's still 1. So where that negative 2 is, we need to have a 1 there to get zeros above it. So we just divide row 3 by a negative 2. So say negative 1/2 times row 3. We use the 1 at A33 to get zeros above it. So negative times row 3 plus row 1, then negative times row 3 plus row 2. The left side gives us the identity. There's more work on the other side. You know, I always had trouble with chalk and with these dry erase markers, like running out of chalk or running out of ink, but this guy, for some strange reason, is running out of whatever. So that doesn't make any sense to me. How can this electronic device run out of electric ink? So let's see. We said negative row 3 plus row 1. So this is negative 1/2 plus 1. We get a 1/2 there. Then it's negative 1/2 plus 0. It's just negative 1/2. And then this is positive 1/2. Then negative row 3 plus row 2. So this becomes negative 1/2. We get negative 1/2 plus 1 is just 1/2. And then this gives us positive 1/2. So A inverse is the 1/2, negative 1/2, 1/2, negative 1/2, 1/2, 1/2, 1/2, 1/2, and negative 1/2. Matrix of 1/2s. So let's see if that's true. So we multiply the first row times the first column. So this is 1/2, 0, and 1/2. We get 1. First row times second column, we get 0. Negative 1/2 plus 1/2, we get 0. First row times the third column, we get 1/2 minus 1/2, we get 0. Even I can do those pretty easy. So then we come down to the second row, first column. So we get 1/2, 0, negative 1/2, and a positive 1/2, we get 0. Second row, second column, we get 0. 1/2 plus 1/2, we get 1. Second row, third column, we get negative 1/2 plus 1/2. With negative 1/2 plus 1/2 is 0. Then plus 0, we get 0. Third row, first column, we get 1/2. 0 minus 1/2, 0. Third row, second column, get 0. 1/2 minus 1/2, 0. Third row, third column, we get a half plus a half is 1 plus 0 is 1. Yay! Now, you do the last one. It's number 5. So we got 7 minutes. Let you do that. You want me to write the answer here? So, oh no, you find it and then you check that with A inverse and see if you get the right one, and then we'll be done. And then on Wednesday I'll review. The test will be on Monday. Okay, let's see. Our time is up, but here's the inverse. You can check it with yours. 7 over 2, 0, negative 3, negative 1, 1, and 0, 0, negative 1, and 1.